Hello learners, welcome once again to Physics Hub 254. Today we want to look at an interesting topic in Form 4, actually the third topic in Form 4. It is a paper 1 question and it reads, a hot air balloon is tethered to the ground on a windless day. The balloon contains 1400 cubic meters of hot air of density 0.7 kilogram per cubic meter. The mass of the balloon is 380 kilogram. Remember, the mass of the balloon in this case is not part of the mass of air inside. So it is just the mass of the balloon fabric itself. So the mass of the balloon, which in this case is the mass of the balloon fabric, is 380 kilogram. The density of the surrounding air is 1.3 kilogram per cubic meter. The first question asks, calculate the tension in the rope holding the balloon to the ground. The second question, calculate the acceleration with which the balloon begins to rise when the rope is cut. So before I plug into a calculation of this question, I always tell students that under this topic, floating and sinking, it is good that before you do any calculation whatsoever, state the Archimedes principle aside, state the law of flotation aside, whether they are in the question paper or not, but a question on floating and sinking is there. These two will help you, give you the road to whatever you are expected to get. So I will first of all have a recap of what is the recap of the law of flotation and the recap of Archimedes principle. So we start with Archimedes principle. It states that a body partially or totally immersed in a fluid experiences an upthrust that is equal to the weight of the fluid displaced. That is Archimedes principle. I'm repeating, Archimedes principle states that when a body is partially or totally immersed in a fluid, it experiences an upthrust that is equal to the weight of the fluid displaced. Full stop. We go to the law of flotation. The law of flotation is just a special case of Archimedes principle. Kind of related, but not that much. The law of flotation states that a floating body displaces its own weight of the fluid in which or on which it floats. I repeat. It states that a floating body displaces its own weight of the fluid on which it floats. So those two, the principle and the law, will now guide us when we are now meeting calculation question, application questions. We'll be looking at them and then we execute. So let us embark on the question. I will represent this question in form of a diagram to bring out the picture. So we have the balloon. The balloon is tethered on the ground using a string. The balloon contains hot air inside. The volume of hot air inside the balloon is 1400 cubic meter. And then the density of the hot air inside the balloon is 0.7 kilogram per cubic meter. mass of 380 kilogram. So the balloon here is tethered using a rope, and therefore, owing to the fact that it has got a low density, we expect an upthrust to be acting on the balloon. So the string or the rope here will experience a tension that is directed towards the fixed point here. That is that. Then the balloon is surrounded by air. That's why we are told that the surrounding air has a density of 1.3 kilogram per cubic meter. Now, let us go to the first question. Calculate the tension in the rope holding the balloon to the ground. Before I even calculate this tension, I need to look at the forces acting on this balloon. 3 forces acting on the balloon is 1, the upthrust is acting on it upwards. 2, we have the tension. And 3, we have the weight, W. We look at the diagram. W, which is the weight, and the tension, they are acting in the same direction. So because the system is at equilibrium, meaning the balloon is not moving up or down, it means the resultant force is 0. So when you say the resultant force is 0 here, we mean the upward force balances the downward force. So we come and say upthrust is equal to weight plus tension. So from there, when I'll be calculating my tension, it means I need to know the upthrust and I also need to know the weight. The weight here comprises of 2 things. 1, the weight of the balloon fabric. 2, the weight of hot air inside the balloon will comprise this weight. So let's now start with the first question. I need to get the upthrust. I know that upthrust is given by volume of the fluid displaced multiplied by the density of the fluid displaced, and then you multiply by G. Because the balloon contained hot air of this volume, it is displacing the same volume of air outside. So I write here 1400. So the 1400 I'm writing here is not the volume of the hot air inside the balloon, but it is the volume of the displaced air outside. Just like, when I dip a stone inside a beaker having some water, of course the water will be given some displacement upward. So that volume is the same as the volume of the stone. So the same to this case. So 1400 times the density of air, which is 1.3, times 10. So this one will give me the upthrust the balloon is experiencing. So allow me to use my phone to calculate this. We have 1400 times 1.3 times 10. I get 18,200 newtons. That is the upthrust, and it is not the answer. Next, we need to get the weight, W. So W here equals to weight of balloon plus weight of hot air. So weight of the balloon, we have the mass of the balloon, from there we can get the weight. It is 380 times 10 plus weight of the balloon will be, you first of all get the mass of the balloon, and you know that mass is simply volume times density. The volume of the balloon is 14, the volume of air inside the balloon is 1400. I multiply by the density of that hot air, which is 0.7. This one will give me mass. So when I want to get weight, I once again, this one becomes 3800 newtons. We add to 1400 times 0.7 times 10. I get 9,800 newtons. So when I add the two, I'll get the total weight of the balloon and its content. So that one gives me that plus 3,800. I get 13,600 newtons. 13,600 newtons. 13,600 newtons. So that is the total weight of the balloon content and the balloon fabric. Now we go to this equation and substitute for us to get the value of tension force. Tension force. So mathematically, this one cross over to this other side, so that we have upthrust minus weight should give us the tension. My upthrust is 18,200. 18,200 less the total weight, which is 13,600, is equal to T. So our T will be equal to, so minus 18, that is 200. I get 4,600 Newton. So that is the tensional force. Final question, the last question. Calculate the acceleration with which the balloon begins to rise. Begins to rise. The word begins is very, very important. Begins to rise. So the rising of the balloon will be as a result of some force, because there will be a net force. Once this one goes off, there will be a net force, meaning the upward force, which is the upthrust, is now even greater. For the balloon to rise up, the upward force, which is upthrust, must be greater than the total downward force, which is this one. And that, we are going to use the tensional force. That difference is now the tensional force. So this string was experiencing some tension, which is equivalent to this. And it's this force that is going to bring that acceleration. It's like this, the net force. Remember in form 3, under Newton's laws of motion, we say that F net equals to mass times acceleration. So this acceleration is what we are looking for. The mass we have. This is the force net. And the net force, or the resultant force, which we've gotten here to be the same as this one. It's the same as the tension force here. So 4,600 is equal to the mass of the balloon is that. The balloon and the content, we must have mass here being the mass of the balloon and the content of the balloon, not the balloon alone. So we'll have 380, we are using mass, plus, this is the mass of the balloon fabric, but inside the balloon we had content, that is the hot air. The hot air also had mass, so we can calculate the mass of the hot air, which is simply 1400 times 0.7, 1400 times 0.7, we get 980, so this is 980. All these are in kilograms, then bracket A. So 4,600 equals 2, so I add the 2, that is plus 380, I get 1360. 1360 A. So divide both sides by 1360 by 1360, so that we get A equals 2. So 4,600 divided by 1360, we get 3.382. We need to give our answers to 4 significant figures for us to be safe. Meters per second square. That is the acceleration with which the balloon begins to rise. Thank you for watching. Please remember to subscribe, like, share, and comment. See you in our next video.